Hey everybody, today is the 6th of September, and we are going to be talking about density. Now, we talked about density a little bit. We talked about it in the context of it being a physical property. Now we're going to expand upon that and do a little bit of calculations of density. Now, one of the important things about density is that it is a physical property that relates mass and volume of a substance. So volume, think about volume as the 3D space that something can occupy, and mass being, well, the kind of weight of something. Now, whenever I'm thinking about density, I always like to think about objects that are nearby me. And let's say that these two different writing utensils. Actually, here we go. I've got a pen and I've got a pencil, mechanical pencil and a mechanical pen. Now, these two substances or these two objects are made of different substances. And, the volume of them is pretty similar to one another, but I can tell that the weight is a little bit different. And so what that means is that if we go ahead and assume that the volume is the same, but the mass is different or the weight is different, that means the density is going to be different between these two objects. So I always try to think about something that's nearby because it makes the idea of density a little bit more tangible. Now, we're going to be relating mass and volume. So the space that something occupies. Here we have an apple with a mass of 172.3 grams. And we have a volume of 45 milliliters of water. So when it comes to density, we can look at density as an equation. D is equal to mass over volume. So it's the mass of something divided by the space that it occupies, the volume. Now the units for density are typically going to be relating the units of volume. So grams per milliliter. So the units for mass and the units for volume. Alternatively, you could have kilograms, kg per liter. Now, is density a physical or a chemical property? Remember, a chemical property is all about how something reacts within the world, whereas a physical property is the way that something exists and you can kind of observe it. Well, what that means is that density is indeed a physical property, not a chemical property, because the density of something is not going to be influencing or influenced by the reacting environment. Now, first, let's look at our different states of matter, because if you think about solids, liquids, and gases, all of your different states of matter are going to have different densities. First, we're going to look at the density of a liquid. We'll then look at the density of a solid. We're not going to get into the density of a gas because gases are kind of tricky, and we'll talk about laws of gases later on. But in the meantime, let's start with densities of liquids. Now, I like this picture right here because of the fact that, one, there's a video associated with it. And we can follow that video, and we can link to that video. It should play. Okay, there we go. Okay. So here what we have is a liquid being added to a glass. Now this liquid the first one that we're going to do is honey. Now you know from your own experience of using honey or eating honey or something like that, that it has it has some unique properties. One, it's a very viscous substance. Next, we're going to add milk. Milk compared to honey, they're quite a bit different in terms of like the texture. We're going to add hand soap. Notice how these things aren't really mixing well with one another because they're distinct. After the hand soap, we'll add some We're going to let the hand soap settle. We're going to add some oil, some motor oil in particular. Notice how the motor oil separates from the hand soap and the milk and rises to the top. Next up, which we're pouring in, basically filling the space, is going to be corn syrup. Corn syrup, well, we've added it and it sinks and it stays close to the bottom. It is going to be above the honey, but below the milk. I think that it's interesting to compare and contrast the corn syrup from the motor oil, because the motor oil went through, but then it raised back up. Vegetable oil goes through, rises up a little bit, but not all the way. So these are different liquids with different densities. Now, if we go back to our presentation, and we look at this mixture, this kind of pause here, we can see that honey sinks to the bottom and stays at the bottom. Motor oil is at the top. So if we wanted to think about the densities of these different things, a dense substance is going to sink. A less dense substance is going to float to the top. So here what we have is honey that sinks to the very bottom, whereas motor oil rises to the top. Now, we can also measure density to identify a liquid. We've got ethanol and water. The ethanol, or the density of ethanol, is 0.79 grams per milliliter. The density of water is 1 gram per milliliter. Now, on our first day in class, or maybe it was our second day, we talked about 1 milliliter is equal to 1 cubic centimeter, or 1 cm cubed. So in this centimeter cubed, what we've got is, we've got something that is 1 centimeter by 1 centimeter by 1 centimeter. And if this was ethanol, it would have a mass of 0.79 grams. If it was water, it would have a mass of 1 gram per milliliter. Now, we want to measure the mass of a liquid in a graduated cylinder. So then what we want to do is we want to read off the volume of liquid in the graduated cylinder. So for this, I'm going to pause so that my recording doesn't include me navigating to the web page. Well, it's good that I paused because I ran into some technical issues in that web page. This link isn't working for me. I think it might be, I don't think it's a Java issue. I'm not exactly sure what the issue is. But what this is right here is an opportunity to measure the density of liquids. Now, the idea is that you would take this graduated cylinder right here and move it onto this digital balance. Place this grad cylinder on this digital balance. And then what you do is you would add a liquid. Let's say adding it to 10 milliliters. And then you would also determine the mass, because the intent is to identify liquids D and E based on their densities. So we take solution, right? We take the water, we'd add it to 10 milliliters, and we'd see that the mass is 10 grams per 10 milliliters. Because if you do 10 grams divided by, so 10 grams divided by 10 milliliters, it would be, well, 10 divided by 10, which is the same as 1. Okay, 1 gram per milliliter. Now, if we were to take solution D, we'd have different numbers. What we would probably want to do is put this grad cylinder, add solution D to this grad cylinder, getting to a total volume of 10 milliliters. Okay, you get to 10 milliliters. So then what would the mass be? Let's say that the mass was 18.0000 0 grams. What would the density of solution D be? Would it say D, or density is 18 divided by 10? Well, 18 divided by 10 is 1.8 grams per mil. So that would be the density of solution B. And that's how you determine the density of a liquid solution, by having a volume and getting the mass of that volume. So now we're going to move on to calculating the density, or observing the density of a different state of matter. In particular, we're going to look at a solid. So what's the density of a solid? To give you a little bit of a spoiler, we're going to use the exact same calculation. D is equal to m over v. Now, the difference between calculating the density of a solid and a liquid is, well, the volume might be a different calculation. So density is, in addition to being a physical property, it's commonly referred to as an intensive property. An intensive property means that if you have, let's say that you have this sheet of copper, or this substance, and then you have this cube of this substance, the density of these two objects is they're going to be identical. So whether you have this huge sheet or this little cube, calculating the density is going to be, or if you calculate the density of these two, they're going to be identical. Okay, so that means this ceramic coffee mug that I have that fits in my hand, if I had a ceramic coffee mug that was this big, or one that was as big as my head, the densities are going to be the same. What's going to be different between them? The mass is going to be different. What else is going to be different? The volume is going to be different, but the density, they are going to be identical. Okay, now great question is, how do you calculate the density of a solid? Well, one easy way that you can do it is, first of all, let's say you take this iron cube or iron ball here, and you put it on this digital balance. You put it on the digital balance and you get a mass of, let's say, 3.2 grams. Okay, first step, determine the mass. Done. The next step is the volume. Okay, volume is the space that's occupied in 3 dimensions. And you might be thinking to yourself, geometry. I remember, let's see, is this like 2 pi r or pi r squared or something like that? Well, the good thing is that we can determine the volume of our substance a little bit more easily than that. What we can do is we can take a graduated cylinder, like what we have right here, put it on this digital balance. And on that digital balance, we'll have something with a designated volume of 200 milliliters. Okay, so that's got a volume of 200 milliliters. Do we need to worry about the mass of this? We don't. What we need to observe is we're going to take this iron ball and drop it in. What do you think is going to happen whenever we drop that in there? Well, one thing is the mass is going to change. And so that's another way that we can determine the mass of that iron ball. But what else is going to change? What happens whenever you get into a bathtub? Well, the solution level rises up. So when you drop this iron ball in, right down there, what's going to happen to this solution level? It's going to go up. And now all of a sudden it's going to be 215 milliliters. And the great thing is that tells you the volume that this iron ball occupies. Let's say it's 215 milliliters. Well, you would be able to determine the density of this object by taking the mass and dividing it by the volume change, or the volume that is the volume of water that is displaced by that iron ball. Now, these numbers right here. In this particular example, I just kind of arbitrarily threw some out there. So if you do that calculation, it's not going to be the density of iron. But the volume for any object. Get a volume of water, get the mass of your object, drop it in, and see how the volume goes up. And how that volume goes up tells you about the density of that object. Now, if we were to look at this, and this would be an example where you calculate the density by looking at the volume. So down here, if this was working, you could take this object, determine the mass of it, drop it in, see the volume that's displaced, and then come up with this calculation. Now, let's say that let's say that it's 27 grams and it displaces the volume 10 milliliters. Then you're looking at a density of 2.7 grams per milliliter. So that object would be aluminum. Okay. Now, measuring the density to identify a metal. Okay, so this is, remember, density is a physical property, so it can be used to identify something. Now, aluminum has a known density of 2.7 grams per milliliter. Zinc has a density of 7.1 grams per milliliter. Here what we have is an object that's 29.5 grams. We take that 29.5, and then we've got to determine the initial volume of our solution. That's about 35 milliliters. Then that volume goes up to, let's see, that's about 30, or 40, not 30, 40 milliliters. Okay, so now let's see. I'm going to use my calculator. 29.5, that's our mass. So using this right here, 29.5 divided by 5. And that would be approximately 5.9 grams per milliliter. Now, with that in mind, looking at either of these two metals, unless I'm reading this incorrectly, we've got 35 and 40 milliliters. It's displacing about 5 milliliters. So if you got this result and you were told that it is either 100% zinc or 100% aluminum, I would definitely want to try to measure this again. But which one is it closer to? It's closer to zinc, but 5.9 grams per milliliter, I would say that it's not zinc or aluminum. But doing this calculation, let's say that this is lead. It's not lead. Let's say that it was magnesium. B equals 5.9. Then I'd be like, okay, well, 5.9 grams per milliliter, it's magnesium, done. That's what it is. Okay. So this is one of the tools that we can use. Measure the volume that's displaced. We have to know the initial volume and the final volume. And then how much of that solution is displaced by that object. And what's the mass of that object? That gives you a mechanism to calculate the density of an object and to then identify it. Okay, so now what I'm going to do is over the next 3 slides, or over the next 2, and then finally we've got this over here, we have a means to calculate, or we have this kind of tool that we can play around with to look at density calculations. So I'm going to change my share to that one. Okay. It's sharing now. I'm going to go to the intro. And with this intro, I'm going to reset it. And reset it. Okay. Now, what I've got is a body of water. And that body of water is, well, it's just pure H2O. I've dropped this object that is wood. I selected that in the upper right-hand corner. And one thing that I want you to notice about this is this compared to styrofoam. It's subtle. It's a small difference, but it's an important difference. That small difference is, here's our square that is, sorry, just a second. Nope, that's not. Here's our cube. Most of it is above the surface of the water. A small percentage of it is submerged. Okay. Now, here are the thoughts. Let's switch it to wood. Let's switch this object to wood. Oh. Now, more of it is submerged. Less of it is above the surface of the water. So what does that tell you about the density of wood versus styrofoam? And think about in your own experience when you've had a wood object versus a styrofoam object. Well, they're different from one another. That wood object, well, it's heavier if it occupies the same space. What do you know about styrofoam? Styrofoam, just toss it up and super light. Now, if we were to switch this from wood down to a brick, well, a brick compared to wood, well, that brick is going to sink all the way. Now, all the while, what we've seen is that this brick that has a mass of approximately 10 grams, which is in the upper right-hand corner here, 10 kilograms, has a volume of 5 liters. It completely sinks, and so it's in good shape there. 100% of that brick is submerged in the water. Now, next up, we can do a comparison. I'm going to reset this as well. Clear all my drawings. We've got object B and object A. They're both 5 kilograms. B is 5 kilograms. Let's look at A in comparison. Now, the question is, do these have different densities? Well, if we want to look at the size of them, they're kind of different in size. Oh, so this block B is big, but it has the same mass as A. A is more condensed. It's more packed in there. It's more dense. Now, if we look at C, what do you think is going to happen with this brick or this block that's C? Well, I'm going to reset this. Now I'm going to say, look at the size of A compared to C and compared to D. Well, brick A, or block A, is larger than C and D. If A sinks, well, then certainly C and D are going to sink. So let's go ahead and try C. Oh, sinks. Oh, D sinks. A and B. Oh, A sinks, B does not. Now, another thing that's observed here is what happens to these different objects and the volume that is displaced by them. So these volumes are different from one another. And the smaller the object, the less space that it occupies, the less volume that is displaced by it. So that gives us a comparison of different objects, and it gives us a way of doing this sort of calculation by volume that's displaced. Now, the last thing that I want to talk about and show you all is this calculation. D equals M over B. Now, if this is a calculation that is important to be able to calculate. Let's say hypothetically, we had an object that had a density of 9.2 grams per milliliter. What you can say about that object is that 1 milliliter of it, so 1 cubic centimeter, is going to have a mass of 9.2 grams. Okay. Now, what if you had 13 milliliters of it? What is the mass of that? Well, it's important to be able to go back and say, well, 1 mil equals 9.2 grams. 13, let's do the calculation. 9.2 times 13. That would have a mass of 9.2 times 13, which is 119.6 grams. Because each milliliter, I always like to think about these things as little cubes. Each of those 1 mil or 1 cubic centimeter cube is 9.2 grams. So if you have 13 of them, you have a total mass of 119.6 grams. Now, what about if we switch that a little bit? And we said, what would the volume of 35 grams of a substance that has a density of 4.2 be? So in this question, what are you asking for? You want to solve for the volume is question mark. Mass is measured in grams. Well, you don't need to know mass because you have it. Density is also provided. So you've got M and you've got D. So the question is, what's the volume? Well, to answer that, you have to manipulate this equation, D equals M over V, and rearrange it to be V equals M over D. Okay, so M is 35 divided by 4.2. Okay, so 35 divided by 4.2, you get 8.33. What's the volume? Well, or the units, I'm sorry. The units are going to be milliliters. So, understanding density, you can expect to see questions that ask you, what's the density of a substance? And in order to answer, let me clear all the drawings off of this slide, actually. In order to answer questions, I'm going to write it above each one of these. This would be, what is density? Down here, what is volume? Then down here is what is mass? Now, with that said, when you see this, if I'm asking you what is the volume, then you need to have and you need to be provided with mass and density. If I'm asking you about mass, then you need to have density and volume. If you're solving for density, then you need M and V. So these are the things that you need to be able to answer based on this information that's provided, and be able to use whatever information that you provided to go backwards to solve for that density. Well, that's all that there is for today. Look out for a quiz/homework type of thing with questions about density, solving for density, solving for volume, solving for mass, and reflect on this slide right here as a guide for how to do it. All right, well, I hope you have a good one, and see you later.